Ouch, guys, I think this is the third video you're watching of me today. That's brutal. I was going through my notes and I had these heat examples that I've already written out. And you know what? They look good. There's some nice coloring going on. They're neat. I feel like if I were to try to do that while explaining today, it might not go well. So I'm going to try something that, well, actually I just did it on the last handout too, is I'm going to talk you through the notes I already have instead of actively writing them down. Now you have a choice. You can write them down as I talk and you look, or you can print up the PDF and work off of that. I think it's better to write it. This is in your packet. It's blank right there. All you got to do is start. Some of you already started. Here we go. An aluminum cube, 5 centimeters on a side, is hung by a string in a boiling bath of water. The aluminum was originally at room temperature. If the density of aluminum is 2.70 grams per centimeters cubed, how much heat flows from the water into the metal if the aluminum cube is left in the water for a very long time? All right. So what did I do? I drew a picture. Here's a metal cube. Then you put it in the hot water. Now, by putting this container full of water on the stove and have it boiling, heat ends up flowing from the stove into the water. Now, why does it stay at 100 degrees? Yeah, go back to chemistry class. As some of those molecules gain even more energy, they go from a liquid phase to a gas phase, and they come off the top as steam. But the water itself stays at 100 degrees Celsius. That's why it's so useful to cook with, because it stays at a constant temperature. Now, if you put the metal block, which in this case was cold, into the hot water, what's going to happen? Well, some of that heat from the hot water is going to flow into the metal cube until what happens? That's right, until it reaches thermal equilibrium. And then they'll all be the same temperature. All right, so this problem is actually very easy. To find that heat that changes the temperature of an object, it's going to be Q equals mc delta T. The mass of the aluminum. Maybe this is why I'm doing this problem. Got to go back to one of the simpler formulas, a formula that is so simple that in years past I've neglected to teach it well. Density is mass divided by volume. I'm pretty sure you spent most of trimester 1 in chemistry reviewing this. No, just kidding. But, you did density. Mass is density times volume. Since it was given in centimeters cubed, those units are going to cancel out. Piece of cake. And you find a mass of 337.5 grams. Now, when I do calorimetry in physics, we're going to be dealing in joules, so we should be dealing in kilograms, and our values for specific heat are in kilograms. They're joules per kilogram, degrees Celsius. So, mass times the specific heat times the change in temperature. That specific heat I got from the chart at the top, which says for aluminum, it's 900 joules per kilogram degrees Celsius. I plug it all in and I get a heat flow of 2.43 times 10 to the 4th joules. Número 2. My bathtub contains 75 liters of water that's become somewhat tepid at 30 degrees Celsius. How much boiling water needs to be added to get the water in the tub to a more comfortable 50 degrees Celsius? We're going to ignore any heat that's absorbed by the tub. Now, why do we have this problem? You know why? Actually, because in my first house, the boiler didn't work right, and the tub was always cold. So when I had to put my daughter in it to take a bath, I'd have to add boiling water to the tub in order for it to be warm enough. That was a long time ago. Now, if I start with a tub with 75 liters of water, Turns out, since the entire metric system is based on a kilogram of water, 1 kilogram of water has a volume of 1 liter, which, by the way, just to throw it out there, is 1 decimeter cubed. That's for water. So, it means we have 75 kilograms of water at 30 degrees Celsius. How much mass would I add of water at 100 degrees Celsius to end up with a final temperature of 50? So if I set up my system, now this is a case where I add two things together and they reach thermal equilibrium. So this is a classic case of the negative heat loss is going to be equal to the heat gain. Now we have the it's the hot water. So mass of the hot water times the specific heat of water times the change in temperature, the negative sign in front, equals mc delta T of the colder water that gained the heat. The specific heat of water cancels out on both sides because it's the same material. I plugged in my numbers. I'm trying to find what is the mass of the hot water. Yeah. All right. So the tub of 75 kilograms went up by 20 degrees. Divide that by the temperature, change in temperature of the boiling water, and I would get that I would have to add 30 liters of boiling water. That's a lot. That's a pain in the neck. Push pause. Write it out. Number 3. Number 3 is tedious. And honestly, it's really not what you're going to see on an AP test. There's just too many steps, too many finer points when it comes to some of the math. It's just tedious. Let me talk you through what I did. This says a 20-gram aluminum calorimeter cup that's surrounded by foam and isolated from the environment contains 45 milliliters of water at 25 degrees Celsius. If a copper sample with a mass of 50 grams is heated in boiling water and then added to the calorimeter, what is the final temperature of the system? And this goes back to what I always tell you guys ad nauseum, which is draw a picture. When there's too much information all spread out, you've got to draw a picture. So I started with my metal sample plus the aluminum cup plus the water will all reach thermal equilibrium at some final temperature, TF. Now the negative Q lost is going to be equal to the Q gained. That's how I approached it this time. If you want to approach it how you did it in chemistry, all the power to you. Push pause. You didn't pause it. Now look, Q lost. This is the key. The Q lost is going to be the change in heat in the metal. That's what lost energy. The Q gained is going to be for the water and the aluminum. That's the key. Okay. Now push pause. Go ahead and copy it down. Work your way through. All right, if you had any questions on that, let me know. Now, this next one, this will be the last one today, is one big, nasty question. I like it. I like it a lot. Here's the thing. In this one problem, we can tie together most of what we have to really understand about heat and calorimetry, at least calorimetry in this unit. Because what we're going to deal with is not just a change in temperature, but also a change in phase. And this graph should look familiar from chemistry class. If not, go back into chapter 14 and read the section that explains this. You'll get it. It's like 3 pages. Here it is. A 5-kilogram block of ice that is originally at negative 15 degrees Celsius is placed in a pot on the stove. If the block is heated until all of the ice is turned into water vapor, how much total heat was required? All right. As you can see from my work, what I did was I drew a picture. I started with my ice at negative 15 degrees. Yeah, ice can be colder than 0 degrees. Duh. You don't think ice is colder than 0 degrees Celsius in the Arctic? Of course it is. Now, when you add heat to that, when you add heat to the ice, the first thing that happens is that the ice increases in temperature. It doesn't undergo a phase change at first. So the ice heats to 0 degrees. Then as you continue to add heat, that triangle under the arrow represents heat being added. The ice turns into water at 0 degrees Celsius. The temperature stays constant during a phase change. Then, as you continue to add heat, that water goes from 0 degrees to 100 degrees Celsius. Once it reaches 100 degrees Celsius, any additional heat that is added into the system goes into changing it from a liquid to a gas, and we end up with water vapor. When I draw the picture out like that, it becomes clear to me that the heat necessary is really, I can break it down into steps. The total heat would be the heat necessary to heat the ice, to melt the ice, to warm the water, to vaporize the water. Now, because I knew I had to graph this, I actually broke it down into different parts. So I'm going to say the energy to heat the ice is going to be mc delta T. Now, the specific heat of ice is slightly different than it is for water. Actually, it's quite a bit different than it is for water. I find that number on the chart on the front of the paper. The heat necessary to undergo a phase change from solid to liquid is also on the front of the paper. 3.33 times 10 to the 5th joules is the latent heat of fusion for water. Then that same 5 kilograms is going to have the specific heat of water, because now it's in a liquid phase, times the change in temperature, which is 100 degrees Celsius. And then lastly, that 5 kilograms is going to have energy or heat put into it until it becomes a vapor. Now you see that LV is much greater than LF, because it takes more energy to go from liquid to gas than it does from solid to liquid. Okay. Once I got all those numbers and added them together, it was a pain in the neck, but I did it in individual steps. And I did that so that I could get a sense of what my total would be and also how to break up my axis. So, down on the graph below, check it out. It says on the axis below, draw in the change in temperature. You know what? I really should have said draw in the temperature, not the change in temperature. Draw in the temperature versus the heat added, making sure to label the axis. Now, I know that it's got to go from negative 15 up to 100. So I counted out my blocks. I started at negative 20, and then I made each block 10. Then I went and looked at the heat added. Now I need to get all the way up to 1.53 times 10 to the 7th. I don't know, graphing with powers of 10 at the end? That stinks. So what I did was that I actually took my axes and I made the units times 10 to the 6 joules. That means in the end, my axis is going to go from 0 to 15.3, oh yeah, times 10 to the 6 joules. But I don't write the 10 times 10 to the, like, I don't write that there. I just leave that in my units right here. So now, when I plot it, I made every two lines 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 times 10 to the 6. When I then plot my points, to go from negative 20 to 0 degrees took 0.158 times 10 to the 6 joules. So 0.158. All right. Oh, yeah. So it's like right here. That's like 0.158 right there. Sort of. Next, 1.67 times 10 to the 6. So I went over 1.67, and while that happened, while that heat was added, the temperature remained constant at 0 degrees until it underwent a phase change, and then it went from this value here, it went up 2.09 times 10 to the 6, or it went up to, so little something like that. And then as more and more heat was added, it stayed at the same temperature until it reached 1.53. Is that my best graphing of the year? Heck no. Josh, don't look too closely. I know. It's hideous. But if I color it in, it might look better. I don't know if that was too fast. I don't know if it was too slow. Either way, it's over. All right, here's number 5, like I promised. I was going through my old answer key, and I realized, oh, that answer was incorrect, and I finally figured out why. A simple mistake. Hopefully you were able to get to the correct answer and find my mistake. If you did, don't watch this video. Go outside. If you're not sure what the heck I did or what's going on, period, watch the video. Number 5, an insulated calorimeter contains 90 grams of water and a 35-gram ice cube, both at 0 degrees Celsius. If an 8 ohm resistor has 30 volts applied across it, sketch a graph of the water temperature versus time for 5 minutes. What do you do? I know what I would do. I would draw a picture. One of the principles you got to keep in mind is when you heat up a mixture like this, something that has both a liquid and a solid phase, if they're at 0 degrees Celsius, there's actually no heat transfer between the ice and the water. That's one of the trickiest things to realize, which means as we add heat to the system, instead of raising the temperature of the water, it's actually going to go into melting the ice. Now, physically, what happens is the water molecules are going to hit the resistor and gain some energy, but then they're going to collide with the ice cube and give that energy up to the ice. Yeah, if you don't believe me, go throw some ice in a cup and watch it. Now, I'm going to start off with a diagram. And in this picture, we have our 35 grams of ice. And that's at 0 degrees, 0 degrees Celsius. And I'm going to have to heat that until it becomes a liquid. So that heat, Q, would be added to the system. When that happens, I would then have a container that would have the 90 grams of water that we started with, plus the 35 grams of ice. Because what's the ice turn into? That's right, water. So now I would have a sample of, what's 35 plus 90? 35 plus 90. Oh, that's right, 125 grams at 90 degrees Celsius. Okay. Oh, at 90. I lost focus. At 0 degrees Celsius. Excuse me. And then I add more heat to the system until one of two things happens. It reaches 100 degrees, or the time runs out, because this problem gives a limit to how far it can extend. Now, because of that, I am going to make a decision. Call it a guess, if you will. Or maybe it's I looked at the answer key first. No, I'm just kidding. Made a guess. I'm going to say it's not going to reach 100 degrees Celsius by the time the 5 minutes is up. I'm just making that call. If I'm wrong, we'll see it in my answer, and I'll have to go back and figure it out. So, what's the graph going to look like? Well, it's going to take a certain amount of heat to melt the ice. Let's figure out how much heat that is to begin with. So when it undergoes a phase change, we're going to have Q equals mass of the ice times the latent heat of fusion. Now, 35 grams is only 0.035 kilograms. And if I look at the chart at the top of this paper, I know that the latent heat of fusion for ice, is, 3.33 times 10 to the 5th joules. So the amount of heat necessary in order to melt that ice is 11655. Now, of course I should round that, but I'm not going to round it yet. I'm going to sort of let that go. So 11,655 joules. Good. What the heck does that have to do with the resistor? Now we have to get into the electrical side of things. How long would it take this system to warm up that ice, or to melt that ice? Now, if I go back and I draw a simple diagram, I know that V equals IR, Ohm's law. I know that power equals IV, and that energy, I'll write it as change in energy right now. You know that's going to be heat. It's going to be IVT. Okay. Now, do they give me the current? No, they just give me the resistance and the voltage. So you know what would be a lot easier? Would be if I took this formula for power and I turned it into V squared over R. Now I'm also going to make that jump and say the heat is going to be equal to V squared over R times T. So what I want to solve for is the temperature. How much time does it take to melt that ice? So I do a little bit of math. I got Q times R divided by V squared equals T. I could have solved for power separately. I'm going with varsity physics today. I got 103.6 seconds. Should I round that to 104? Probably. Yep, you're right. You're right. 104 seconds. Let's go back up to the graph. What the heck does that mean? Well, what it really means is that the temperature is going to stay at 0 degrees until 103.6 seconds. And at that time, all of the ice would have melted. Now I have a sample of water that is going to be heated by that resistor. Okay, so the question is, what will be the final temperature? Will it be 100 degrees, 80, somewhere here? What I do know is that the line should be linear. I just don't know where it ends, because as you heat it, it heats in a linear fashion. So I got to find the final temperature. Find the final T. Okay, well, I know that to heat up the water is going to be MC delta T. How much heat would be required? Wow, wait, I don't know what the temperature final is. Shoot, I don't know Q or delta T. What do I know? Well, I know the time remaining. If it's going for 5 minutes, I know that that's 300 seconds. So the delta T that it's going to heat up the water is going to be 300 minus 103.6. Now, pre-coronavirus, you guys would all be staring at me saying, oh, that's it? That's how you do it. Now I got it. And then you would stop listening and you would just go ahead and solve it. I know that. But since you're at home, I don't know, maybe you're smarter. Maybe you have no idea what I'm talking about. I don't know. But what I did was I found the time remaining for it to heat up. If I know that, I can find the energy that's going to be transformed by the resistor into heat. I can find change in energy. So if I do that, change in energy is power times time. Oh wait, same substitution, V squared over R times time. Now I know what the time is. I can find out how much of that energy is produced. And again, we're assuming no loss of energy to the environment. All right, so I got 22095. You get that? Probably not, because I bet you don't have any calculators out. No, I'm just kidding. I'm sure you do. Amanda, did you get that? You're the one I usually check with. 2,295 joules. Now that is Q. So I'm going to take that value and plug it in back up here. So let's do it. So Q equals MC delta T. Q equals MC temperature final minus temperature initial. Yeah? You okay with that? Yeah, of course you are. It's just a change in temperature. If you're not, don't admit it. You can do that. Now, oh yeah, the temperature initial is 0 degrees Celsius, so that makes things easier. So if I were to write this as Q equals MC temperature final, Q divided by MC, 22095 divided by 125 times 4186 gives me a final temperature of the system. Divided by 125 times 4186. Please be right, please be right, please be right. Oh, snap. I got 0.042226. That can't be the final temperature. What did I do wrong? Check plus. Who's got it? Who sees it? Speak up. Nice. Thank you, Charlotte. You're right. 0.125. Yes. So I take that and I got 42.2 degrees Celsius. Now, there could have been rounding somewhere along the way. We don't fight about it. But that is our final answer. 42.2 degrees Celsius. Now, for those of you that got that right on your own, that is awesome. It's awesome. So I'm going to go ahead and plot at 300 seconds. We would have 42.3. I'm going to connect that line. It's going to be a beautiful linear line. Now, when Dr. Lupini said 30 minutes per class, 20 or 30 minutes, I'm not sure that he fully realized that this is AP Physics too. You guys are brilliant. Well, you're smart. You're hardworking. And problems take 12 minutes. Sorry, it does take a while. I hope you got this on your own. If you did, I'm going to write that in the attendance that you need to tell me you figured this out on your own. If you didn't, it's okay. You're a high school student. Life goes on. I hope you guys are good. Thank you for working through this today. Hopefully you didn't even watch this video because you got it. All right, I'll lab tomorrow.